For a long time, atoms were thought to be the final, indivisible building blocks of matter, tiny, solid particles beyond which science could not go. But the moment scientists asked what was inside an atom, chemistry crossed into an entirely new dimension, one where invisible structure explained why matter behaves the way it does. This is the Learning Studio, where we don't just accept scientific models, we trace how they were discovered and why they changed everything. And in this chemistry series, each idea builds directly on the last. So once atoms are understood, the next logical step is to look inside them. Most people think the structure of the atom is just a diagram with dots and circles, but in reality, it explains electricity, chemical bonding, radiation, and even modern electronics. For example, when static electricity makes your hair stand up, or when a phone battery powers a circuit, what you're witnessing is atomic structure in action, the movement and behavior of charged particles inside atoms. The first crack in the solid atom idea came when Thomson discovered the electron. By studying cathode rays, he showed that atoms contain tiny, negatively charged particles far smaller than the atom itself. This meant atoms were divisible, and more importantly, that electrical charge was built into matter at a fundamental level. If electrons existed, something had to balance their charge. That question was answered when Ernest Rutherford conducted his famous gold foil experiment. By firing alpha particles at thin sheets of gold, he discovered that most of the atom is empty space, with nearly all its mass concentrated in a tiny, positively charged nucleus. This overturned earlier models and revealed the atom as a structured system rather than a solid sphere. The nucleus itself soon became clearer when scientists identified protons as the positively charged particles responsible for an element's identity. The number of protons in the nucleus defines what element an atom is. Change the proton count, and you change the element entirely. Later, the discovery of neutrons explained how nuclei remain stable despite the repulsion between positively charged protons. To explain how electrons behave around this nucleus, Niels Bohr introduced the idea that electrons occupy specific energy levels rather than moving randomly. This model explained why atoms emit specific colors of light and why chemical behavior follows consistent patterns. Although later refined by quantum mechanics, Bohr's model gave chemistry its first predictive atomic framework. Once atomic structure was understood, chemistry became far more than descriptive. The behavior of elements, the formation of ions, and the way substances react could now be traced directly to the arrangement of protons, neutrons, and electrons. Atomic structure became the bridge between physics and chemistry, linking subatomic particles to observable chemical behavior. And once we understand what atoms are made of and how their internal structure determines their behavior, the next unavoidable question arises. If electrons control interactions between atoms, then why do atoms join together at all? That question leads directly into the next episode, where we explore why atoms form chemical bonds, the force that turns atomic structure into molecules, materials, and life itself.